Random sampling. Random sampling plays an important role in the design of economic mechanisms. For example, during elections, polls that predict each candidate's ranking affect the results of the elections, and in many settings, market analysis and user studies using a small random sample of the population can lead to good decisions in product development and pricing. In this section, we consider a natural extension of the empirical Myerson mechanism that uses random sampling to address the consistency issues raised in the preceding section. Definition 13.25 Random sampling empirical Myerson. The random sampling empirical Myerson mechanism, RSEM, works as follows. 1. Solicit bits B equals to B1, B2, B3 until Bn to partition the bits into two sets B prime and B prime prime uniformly at random. 3. Compute empirical distributions for each set F prime equals to FB prime and F prime prime equals to FB prime prime. 4. Run a Meyer F prime prime of B prime and a Meyer F prime of B prime prime. For digital goods auctions, we can replace steps 3 and 4 by their more natural interpretations, facilitated by the shorthand notation OPT of B equals to OPT of F of B. 3 prime. Compute the optimal sale price as P prime equals to OPT of B prime and P prime prime equals to OPT of B prime prime. 4 prime. Overprice P prime to bidders in a B prime prime and price P prime prime to bidders in B prime. We refer to the digital goods variant of the random sampling empirical Myerson mechanism as the random sampling optimal price auction, RSOP. The randomization in RSOP allows it to bypass the deterministic impossibility for worst-case settings, leading to the following theorem. Again, this is as a corollary of theorem 13.30, which is proven in the next section. Theorem 13.26. For B with BI in the closed interval between 1 and H, the expected revenue of RSOP approaches that of the optimal single price sale as the number of bidders grows. Similar results do not necessarily hold for more general settings. It is easy to imagine situations where RSEM also gives infeasible outcomes, as the following example illustrates. Example 13.27. Consider the setting where we are selling a digital good in one of two markets. For convenience, bidders 1, 2, 3 until I are in market A, and bidders I plus 1, I plus 2 until N are in market B. Due perhaps to government regulations, it is not legal to sell the good to bidders in both markets simultaneously. Thus, feasible solutions will have winners either only from market A or only from market B. It is easy to construct settings where RSEM will sell to one market in B prime and the other in B prime prime. The combined outcome, however, is not feasible. The biggest open problem in prior free mechanism design is to understand how to approximate the optimal mechanism in more general settings.